coming. This is a invited talk sponsored by the Research Center of Internet of Things. Today we have speaker Professor Shervin, Shirmohammadi.
Yes.
From Ottawa. He is a full professor and also an actuary fellow for his contributions to multimedia systems and network management. He has led a very big research group with many PhD students and also other faculty members within the group. And also he has several years of working experience in the industry. So I'll leave the time to the speaker, and please join me to welcome Professor Shervin once again. Thank you.
Thank you very much for the introduction. So in today's presentation, I would like to talk to you about future computer networks, specifically self-healing networks that can autonomously fix themselves and show super intelligent traits in doing so. So this is a project that I've been doing with the networking company Sienna since 4 years, specifically with their Blue Planet division, which is about network analytics. And today I'm going to show you how we use machine learning to not only detect and localize faults in the network, but also suggest solutions to fix those problems. And I'm also going to show you how we use reinforcement learning to come up with a system that can suggest solutions that are even better than the human expert rules or the human solutions.
Is it a Canadian-based company?
Sienna is actually an American company, but the majority of their R&D is in Ottawa, in Canada.
Okay.
Yes.
Yeah,
Yes.
I see the name ends with NA, which matches to Canada.
Canada, yes. That's right. So, first of all, what is a network operations center? So we know that today the communication service providers, they operate the internet core, which is about 9 billion customers and rising. They also operate other networks to support voice, content delivery, Internet of Things, inter-office enterprise connectivity, payment top-up services, and so on and so forth. An example in Taiwan of such an operator is, for example, Chunghwa Telecom or Taiwan Mobile Telecom. These operators, they have to first of all make sure that they honor the service level agreement that they have with their customers, so they have to provide the correct quality of experience to their customers, but at the same time they want to minimize the operational expenditures or OPEX in order to be profitable and make money. So in order to achieve all of that, they do have teams of network professionals in what we call a network operations center, which monitors the network's status and operations. I will show you a picture of that in the next slide. Typically in these operations centers, we have people who do things manually, because when things happen for the first time, nobody knows how to fix it. They have to do it manually. And in very simple cases, they can do it with previously prepared expert rules. So if the issue is trivial and it has been solved before, they can use the expert rules. But if it's not, then it's a problem. So these technicians, they are on call 24 hours and 7 days a week to make sure the network is operating at all times. And it's actually, when a non-trivial issue happens, for example, something goes down, suddenly the network goes down in some point, or people lose internet access, they quickly have to resolve it. So they have specialized support teams organized by technology domains. For example, oh, let's go talk to the fiber optic guys. Oh, this is a 5G problem. Let's go talk to the 5G guys. And then when you go talk to the 5G guys, they themselves have to communicate with the equipment vendors. Let's talk to Cisco. Let's talk to Nokia. So it becomes really complicated very quickly. And here you can see that this is the actual network and the raw data is coming. The operator makes a decision based on ticket or raw data. They do use network analytics, and then they take actions. And what we are suggesting is that this ARE, which is the action recommendation engine in machine learning, this should be taking actions autonomously. So here you can see this is an actual network operation center in Italy. it's getting more and more expensive to run these NOCs, and it's getting more complicated to operate them as the networks are getting larger and larger. All these IoT devices and everything is being added. So the amount of losses, economic losses, are also rising. In the past 7 years, costs have risen 32%, and downtime now tops 1 million for 44% of businesses. As an example, a while ago in Canada, we had a failure by one of our largest providers, Rogers Communications, and it was just down for a few hours, but nobody had internet access, nobody had mobile access, and in those few hours, the economy lost $150 million. So that's a lot of money. And the reason it took so long for them to fix it is because the issue was not trivial. So if we can automate these things, it should be faster to recover. And there have been attempts to automate these things, but it's very difficult because you have to come up with expert rules that work well in complex networks for situations you haven't seen before, and that's not easy. Also, no single person is aware of all the rules. That's why you need a collection of people. So this was a motivation for our research. The motivation was, if the NOC problems are solved by the collective human intelligence, can we replace that by artificial intelligence? And the rationale is that, yes, it's a complex network, but even in complex network, there is a logical relationship between a problem and the remedial action. Now, as the network gets more complex, it's difficult for humans to see those relationships, but AI may be able to see those relationships much easier. So this is why we decided to study if AI can replace the collective human intelligence. So we emulated exactly how the NOC works in the real world, which is that first they detect the state of the network. Is the network operating normally? Is there a problem? If there's a problem, where is the problem? And once they have that, they go to an action recommendation. So, okay, now what we do to fix the problem? So we created a machine learning module for this, the NSD, and we also created a machine learning module for this, the ARE. And we tested them. So let's start with the first one, network state detector. So we created a network that looks like an ISP network, more or less. And we collected all the quality of service, quality of experience metrics. And we tried to detect the network state. So at 20 days, we collected data over 20 days in 56,000 data points. And we defined what is congestion. We defined what is network physical issue, what is a problem, if delay and jitter are ranging between these numbers. So we define all of those things. So those indicate network problems. And then we just let the network run for 20 days. It's actually a GNS network, GNS3 network. And we collected the data set of these points. And then we trained our machine learning module with that data set. We used simple decision trees. We also use two ensemble methods, gradient boosting and extreme gradient boosting. But one of the problems we encountered is that most of the time there is no problem with the network. So the state is normal. So the machine learning module biases toward this majority class. But in fact, it's the minority classes we are interested in. So we overcame that with ensemble methods. And the result was pretty good. The network state can be determined by more than 90% accuracy. And this is the first stage. So we detect the network, there is a problem, and where is the problem? So now the second stage is, okay, how do we fix a problem? So in order to do that, we ask Sienna to give us the expert rules. So this is the expert rules for this specific network that we have. And we again, let the network run and take actions according to the rules. So that's how we collected the data set. Of course, we define costs and benefits of actions have benefits and costs. And by the way, in case you're interested, the user here are just downloading files from a cloud. So that's the quality of experience we are measuring. Again, we had the same issue. The majority of time, there is nothing to be done, so the recommended action is do nothing. We are interested in this, so we also solved that problem exactly the same as before. And we were able to get a very good result. So 91%, here you can see, the machine learning module can give you the right recommendation for the problem. So this is good. So we said, okay, let's now deploy it and run it and see what happens. So we put it again on a emulated network. We let it run for 10 hours. And the red line that you see, this is the performance. And this is, of course, as time is going by. The red line is the human expert rules. So if you let the expert rules run the network, this is the performance that you get. And our XGB, or extreme gradient boosting method, is the blue line, and you can see it very closely follows the expert rules, which is very good. So this proved that the machine learning module can automatically detect problems and fix problems at a level that is very comparable to humans. Now, in this example, the network is not that difficult. Oops, the network is actually a little simplistic, not too simplistic, but a little simplistic, because these are still autonomous systems. But the conclusion still holds, because as things get more complicated, it actually gets even more complicated to come up with the expert rules. And machine learning will definitely help in that regard. So that was very nice, and we were happy with it. But then the question came about, well, it only follows the expert rules. It very closely follows the expert rules. Can it do better than expert rules? This is the question that we wanted to actually address. So is there a potential to outperform the human-defined rules? And the reason we asked that is because this will be a superintelligent system, and it has already been shown that such a superintelligence is achievable in the realm of computer games, at least. So there are some studies that have shown that. You probably know about this machine learning module that can beat any Go player on the planet, even the Go champion. So that's a sign of superintelligence. Can we have a network that comes up with rules that are even better than the human rules? So this is what we wanted to study. And for that, we decided to use reinforcement learning, because reinforcement learning learns by itself. From trial and error, it actually learns by itself. So we use the same network. It's actually mirrored, but it's the same network. However, we made it more challenging by adding video feed. Instead of downloading files, it's video streaming. So here are clients watching YouTube or watching Netflix, and this is the cloud of YouTube or Netflix. And we made it very realistic. We use the Dash protocol, Dash streaming protocol. This protocol actually changes the bitrate of the video according to how much bandwidth you have available at the moment. So it actually gets quite complicated and dynamic. And again, we defined different metrics. So there is Dash players in Docker containers running. We actually use multiple adaptive bitrate. ABR is adaptive bitrate algorithms. So it wasn't just one fixed bitrate, but different ones. So for example, if you're watching YouTube and Netflix on the same network, so it's a mix of different protocols, how does it behave? So it wasn't homogeneous, it was actually heterogeneous. It was multiple things. We defined what's a transient problem, persistent problem, recurrent problem, and so on and so forth. Then we defined the goal is exactly the same. So maximize the quality of experience minus the operational expenditures. For quality of experience, there are well-known metrics to measure the video quality of experience. We use this one specifically. This one is a combination of the actual bit rate, how many times you change the bit rate, so the switching between different bit rates, what is the buffer level at the client, and so on and so forth. So it actually measures quite a few things, and that gives you a number, which is a quality of experience. But to make it simpler, we kind of normalize that number between 0 and 5, mimicking a 5-star rating system. So 1 to 2 stars are low quality of experience, 3 stars are medium, and 4 to 5 stars are high quality of experience. So you get +5, which is high quality, 0, which is medium quality, so no reward, and -5, which is bad quality, so you actually get punished, right? Remember, this is reinforcement learning. It's all about punishment and reward, right? And OPEX was a simple sum of the cost of performing an action, number of hop counts, because as you go from hop to hop, the cost of transmission increases, and also cost of carrying traffic through the backup ISP, which is the autonomous system 3. That's a backup ISP. You use it only when your own network fails. So, but you're going to have to pay more price for that as well. And the final reward is simply the sum of all these gain metrics, the sum of all this gain over a horizon of H. We actually chose 100 steps, so it can actually look into the 100 steps into the future, if you will, to try to guess what will happen. So this gamma is defined based on that 100, and it's actually 0.99 when you calculate it. So that's the reinforcement learning part. And there was a practical issue. The practical issue is this. A reinforcement learning agent, it has to learn by making mistakes. Right? It makes mistakes and it learns, so it tries to improve. But in a real network, you cannot afford that. You cannot deploy it and say, oh, it made a mistake and now half of Taiwan doesn't have internet connection. That's unacceptable. So what can we do to avoid that? Well, we came up with 3 different things. First of all, similar to the previous part of the project, we use a GNS3 environment for running things in an emulator. But the problem is that this is extremely slow. So what we did, we created a simulator environment that I will tell you later. And we also introduced the idea of batch RL environment, which is actually kind of like, you can think of it as supervised learning for reinforcement learning. I will tell you what it is. So the GNS3 is exactly the same as before. I'm not going to spend time on it. It's just an emulator environment, and people who have done network simulation and emulation, they know what it is. For the simulator environment, what we did was we actually let it run in GNS3 for a long time, you know, a couple of days, 3 days, 4 days, 5 days. And then we took the data and we saw what is the probability of going from, you know, state S to state S hat, and which action is causing it. So we actually analytically calculated those probabilities. And based on those probabilities, we created the simulator environment that says, oh, if you take this action, the highest probability that your state is going to be in is this state. So this is going to be your state, for example. Or it actually randomly generates that state. This turned out to be very interesting. So this simplifies the network into an analytical mathematical model, a purely mathematical model. And it was very, very good because then we could run things extremely fast on it. So for example, 4,167 hours of real time, we could run it in just 6 minutes, which is extremely fast. So that's very good. The other problem is that sometimes an operator doesn't want you to have, you know, doesn't want you to run things anywhere, or doesn't want to collect all that data and create a simulator out of it. But they do have traces already. So what we can do is that we can let the reinforcement learning agent learn from the traces without taking any actions. So this is a part that we contributed. I hadn't seen it before in reinforcement learning. So the agent actually looks at, okay, this is the state, this is the action, and this is the reward. But it doesn't take actions itself. It cannot, because this is the data set trace. It's already done. Things are already done, right? So that was very interesting too. So you can actually learn from that as well. Okay, so with these 3, this is the RL architecture. I'm going to skip over it. It's just how, you know, the parameters that we chose in the interest of time. And these are the expert rules that, again, Sienna gave to us. I don't know why it keeps jumping like that on me. This is the expert rule that Sienna gave to us, again, for this network. You can see it's starting to get a little bit more complicated, even though the network is not that complex. So you can imagine how complex it will get if the network actually grows. And so what we saw was very, very interesting. So this is the gain metric that I told you about. And the orange line is the expert rules. So this is the human rules. And you can see that the reinforcement learning agent, you know, starts to learn, and then it starts to do better and better and better and better over time. And it does it really well. And here I'm also showing you the reward function in case you're interested on the reward function itself. This, by the way, was pre-trained using the synthetic data on the simulator environment. So this we could do very quickly. So we let this run for a little bit longer, and you can see that it's actually quite stable. It doesn't collapse. So the blue line is our agent. It continuously does better than the human-defined rules. And that was very, very interesting to see. So we looked into some details. We wanted to see why it's doing better than human. What is it doing exactly? So first of all, you can see that these are actions taken by the expert rules, and these are the actions taken by our agent. And you can see it actually takes fewer actions, which makes the network more stable, right? And the second thing, if this is the buffer level of the videos, the different video streams, and you can see that it fluctuates quite a bit with the expert rules, but it's a lot more stable with the agent. So then the question became, why? What is it doing? So we looked into that. So we saw three interesting things. The first one is that it ignores any network issue that is not likely to affect any client. Like what? For example, if the path is empty and there is a problem on that path, just let it go. There's no traffic there anyway. Or if the problem is transient, if it predicts the problem to be transient, it's not going to do anything for a while, right? But this you cannot say is super intelligent. This also, the expert rules have very similar rules to that. This is the part that was really, really interesting. It figured out by itself that if it puts all the traffic on path 1, all the video streams on path 1, then it achieves the highest quality of experience and the lowest cost. And this is counterintuitive. A human operator would not put all the traffic on one path because there is a danger of congestion. But the RL agent realized that, well, because of the way Dash operates, it takes down or up the bitrate of the video. The Dash will, if it puts everything on one path, Dash will bring all the videos to 3,134 kilobits per second, which is exactly enough bandwidth for exactly enough bitrate for that path, and is exactly enough bitrate to achieve the highest quality of experience. So it actually figured this out by itself without any expert rules. Now, can we say it's because of that it's super intelligent? Not necessarily, because a human operator eventually would probably guess that, right? However, it is showing super intelligent trait, meaning that it's figuring out things that nobody has taught it. It's coming up with rules that nobody has taught. So that's interesting. And the other thing it did is that it paid attention to links that are shared between different paths. It quickly fixed those links if they became a problem. So we also ran it on the batch RL environment that I told you about, just to show you. So for the first 400,000 steps, we didn't allow it to do any changes, just observe and do what you know. So that's all it did, and it exactly monitors the expert rules. From 400,000 steps, we allowed it a little bit to explore, explore a little bit. And you can see that from that point on, it started to gradually become better than the expert rules again. So that also was very interesting for our partner. Just to wrap up the talk, so the limitations that we came up with, so this was very exciting, and we said, okay, let's go and deploy this and commercialize this. So we went, and our partner Sienna does not have its own networks. It's a networking company, so it makes equipment for other customers. So we went and we tried to get customer data. Some didn't give, some gave, but the problem was finding a high quality data set was very, very challenging. The data sets that you get are very low quality, and you say, okay, there is a problem here. How was the problem fixed? Well, this is what the ticket says. I sent it to Joe and he fixed it. Okay, that's very useless information. How can you train the machine learning agent like that? So that was our problem. However, the project is still ongoing, and by the way, other companies have started to come up with tools that do exactly what we envisioned to do. So that's actually promising to see. Although, unfortunately, we are not first in the market anymore, but to see that this is actually going to the market by some other companies is very encouraging. And we also patented it. Thank you very much, and I'll be happy to answer any questions you might have.
Thank you for this very interesting and encouraging talk that brings
Thank you.
AI machine learning into the real world problems. So I think we can take questions from the audience. Anything you want to know more from the talk? Yes?
Professor Shervin, thanks for your fruitful talk, and I think it inspired us a lot. And I just have a quick question about, since you mentioned that you adapted reinforcement learning, right? So I think the key part about the reinforcement learning is how to do a balancing between the exploitation and the exploitation. So could you just give us more, maybe the example based on your current vigor to show how to realize that? Yeah, thank you.
Thank you very much. Yeah, so exploration is perfectly okay to let the machine explore in the emulation environment or in the simulator. So you can just let it go crazy there, no problem. But you are absolutely right. It's very, very important to make sure that it's not doing anything too wildly in an actual environment. So this is why here we gave it the room just to do a little bit of exploration. So that you can actually set. I don't know the exact details of how we try to balance the exploration in the wild scenario, because if you let it go too wild also, it might not get to the optimum result. But what we did take care of that, yes.
Another thing is about the complexity part. Mm-hmm. So I think if you want to run reinforcement learning in real time, right? So is it enough for your current result, or you need to try to accelerate the reinforcement learning part? Just additional question, yeah.
Yeah, that's an excellent point. Actually, you can see this network again. It wasn't that. Oh, I keep going backwards. Sorry. This network wasn't that complicated, so there was no problem here. We could actually do it, but then another project we did with the same partner is, okay, what if it's a really large network? And what we did for that is that we haven't published it yet, so this is why I'm not showing it. But what I can tell you what we did approximately, which is we actually came up with some sample topologies. So this is one topology. So you got a trapezoid and a rectangle. And a triangle, right? So we came up with a few small topologies, different ones, and then we trained different agents on different topologies. And then when you have a larger network, you can actually have these multiple agents taking care of their topologies at the same time. So that was actually patented. I think this is this patent. Oh, sorry. Yeah, this one. Creating a global reinforcement learning model from subnetwork RL agents. So that's how we address the issue of complexity, because you're absolutely right. If you have a very large network, one agent cannot handle the entire network. That's correct.
Thanks for answering.
No problem, my pleasure.
Any more questions?
Yes, there's one here.
Yeah.
Can you explain about the experiment which compared to your model? So can you take an example, the experiment?
Yes, so the expert rule is actually right here. So this is actually the entire expert rule. So it tries to do things like, if it's congested, you do this. What path is congested? Go to the other path, for example. If there's a quality of experience issue, then what you do. So these are, you can actually follow this algorithm for the complete expert rules. And then in the other sub-project, I also had a set of expert rules. And the point is that, this is not easy even for a simple network like that. And as the network is more complicated, this actually becomes extremely complicated, and it has to be automated.
So myself I can see, it seems to me that from your results, the human beings are doing too much when making decisions. You can see that the decisions makes the network fluctuated, and machine learning can more stabilize the network. Yeah, exactly this one. But so, could you can the results from machine learning help to
make better decisions for human beings.
Can we get some help from them? Yes, absolutely, absolutely. So one of the things you can do is you can now use this as the baseline for your expert rules. So you can translate that into expert rules and into. The only thing is I'm not sure if it can be written like this anymore. Yeah, but it can be written as a mathematical model at least, which should be able to be transferred into an algorithm, theoretically speaking. Yeah, but yeah, that's a good point.
How much time we have?
We are 2 minutes over.
2 minutes over time. Okay, so if you have more questions, I think the audience, the speaker will be happy to take questions offline. So we appreciate your excellent talk again, also your attendance. So let's thanks once again.
Thank you.